So here's the main thing. We started chapter 4, and I'm very honest about it. It's the toughest, driest chapter in the book. It's our goal is to get through this chapter and still be on speaking terms, okay? So that's a two-way street. We'll see how it goes. The main thing is to understand limits and continuity. There'll be a few other things about maxes and mins and how you can generalize those and make Riemann integrals super general. But for engineers, it's just kind of a cultural thing. It's not a practical thing. We had two preliminary definitions. So if you want to take the limit from the right at a point, we would start, say, here at x equals 3 and move x closer and closer to 2. That would cause the function values to rise and rise and rise and rise. Now, if we take the limit as eta goes to infinity of f of x0 plus 1 over eta, we never make it exactly to x0. So we don't have to worry about the fact that the function has a jump here. We never evaluate the function at the point x0. So that's the limit from the right side of the point, and here is the point 2 we were looking at.
But there's no, like...
We can take that same point and look at the limit from the left. So I don't know, let's just start here at 1 and get closer and closer to 2, but never reach 2. Here the function values are constant. Whoops. So it's quite easy to see what the limit is going to. But once again, we never reach the function value at 2 because x is never equal to 2. Here we're using our knowledge of limits as a variable goes to infinity. But we know that 1 over the variable, as the limit goes to infinity, that means 1 over eta is becoming extremely small, and it's going to be small and positive because eta is going to infinity. And if we let eta go to minus infinity, then 1 over eta is negative and very small in magnitude. Okay, so, but it never equals 0 because we never achieve minus infinity. Yep, the t-shirts are free for the taking. There's 2 mediums over here on the end, if that's what you're looking for.
I haven't gotten
I think
it
the
yet.
smalls were all collected. Do you have any?
No, they're small.
Oh, okay.
You're far right. Oh, this one?
No, that's XL.
Right.
Other left.
Oh, right. Yeah.
No, that's medium. The one
Yeah, the middle right.
middle. There we go. Okay. So now we're going to work towards the formal and more common definitions. Okay, so if 1 over eta, as eta goes to infinity I said, not 0, we're going to replace that with h goes to 0 plus, which means h greater than 0, h small. And then similarly in the definition, when we're using limits at infinity and using this quantity 1 over eta, and let eta go to minus infinity, that's replaced with, we're going to use the symbol h goes to 0 from the left instead of the right, so that's 0 minus. That means h is negative and the magnitude of h is small. Okay, if I just said h is small, then minus 250 is smaller than minus 1, okay? So the magnitude. Okay, so all we're going to do is take this notation and put it into this concept. And it's still the same idea. We approach, don't evaluate at the particular points. And for certain things, it just doesn't matter because the function is continuous there. And that's what's going to give us the formal definition of continuity. And so definition, and these are one-sided limits at a point. Suppose we've got some interval AB with x in the interval, and a function f defined on the open interval AB, except possibly at x0. And maybe to emphasize it, we'll say x0 itself. So this is just verbiage to represent this picture. We could even have the function undefined at these points and we just wouldn't care. Okay. Let L be a real number. That means it's finite. Then limit x goes to x0 plus, so from the right of f of x is by definition equal to limit as h goes to 0 plus of f of x0 plus h. So all we've done here is replace 1 over eta for eta large and positive by h, where h is going to 0 from the right. So it's going to 0 through positive quantities. And then this is equal to L if, and now it's the favorite letters for all engineers, for all epsilon greater than 0, no matter how small. There exists delta, which can depend on epsilon, positive, such that if I compare f of x0 plus this little perturbation h to the limit, it's always within our level of precision, epsilon, for all h that are positive and less than or equal to delta epsilon. If approaches L from the right. Excuse me, approaches L as h goes to 0 plus. It's a better way to write that. Which is from the right. Okay, and if we were just looking at our picture here, you give me a level of precision, and then I can back that up to bounds on x. So that's the delta epsilon, the little bound on x, whereas epsilon is how close we are to the limit, which in this case would be 1. Okay, so it's just saying, whereas if you try to take a point here, no matter what you do as you perturb away from it, the function value is far away from there. You can't make it close. Okay, so that's what's going on. Oh, you weren't supposed to do that. We'll undo them this way. Yep. Hopefully I didn't undo too many things here. No. Okay. And similarly, limit x approaches x0 from the left through smaller values of f of x. This by definition means we take the limit as h goes to 0 through negative values of f of x0 plus h, and that's equal to L. And it's essentially the same thing we said here, except we're going to have h being negative and small. And so we'll have f of x0 plus h minus L is within our level of precision epsilon for all small negative values of h. F approaches L as h goes to 0 from the left. Never evaluate f at x0 when computing limits. Okay. So in the textbook, I've got some code that you'll get to play with in Julia as well. Well, open. Let me blow this up a little bit. Okay, so just take eta, and here, you know, from 100 to 10 to the power 4, and I'm going to let h on the right, which is positive values, just be 1 dot divide eta. So that takes 1 and makes a vector that's the same length as eta, but this is now little bitty values, and you can evaluate a function at that, and you can plot it. You can do the same thing by h's to evaluate from the left by just doing minus what you had from the right, and you can evaluate your function, and you can plot all that stuff. And so you can visually check. So if an engineer has a really hard problem, that's probably what they're going to do. We're going to do the actual epsilon delta calculations for 2 toy examples. Okay, but your functions can be arbitrarily complicated, and you may have to play with different values of eta, et cetera, but the whole idea is this is an easy way to generate small values of h, perturb the function about a limit point, and then find out what's going on. Okay, so. First one, f of x equals square root of x minus 3. How do we go about, and what I want to do is just break it down instead of just grinding through the numbers. Let's actually just think about it. Okay, so square root of x minus 3, we're working in the reals, okay? So not complex numbers. So what's the domain of square root of x? X greater than or equal to 0. And so for negative numbers, we have a problem. So what if x is on the left of 3? If it's to the right of 3, it's bigger than 3, then we've got something positive. So we can look at the limit as x decreases to 3. But if we start over here at 1 and increase to 3, we're always going through negative numbers. So that limit cannot exist, okay? So we observe that the limit as x goes to 3 from the left of x is undefined. Because square root of y is undefined for y less than 0. Okay, so that's, once again, working with real numbers. If you want to allow the imaginary unit, then we can, do negatives and do all sorts of things, but we're not doing that. Okay, so it's working with real numbers. Now, suppose we start at x at, say, 3.1, and we start decreasing towards 3. What do you think the limit is? Yeah, okay, perfect. Okay, so I'm going to put suspect because we don't have any epsilons and deltas yet. Okay, we're going to get the epsilons and deltas. We suspect limit x goes to 3 from the right of f of x equals 0. So if you have to work these problems, we set x0 equals 3 and L equals 0. We seek for all epsilon positive a delta sub epsilon positive satisfying the definition. Okay, let you get caught up, and we're going to write down the definition, the abstract thing. Okay, so I'm not trying to turn you guys into mathematicians. What I want is that you're not afraid of this level of analysis, that you can look at it and say, oh, I know what's going on. That's really what we need, that we're comfortable with it. Even if we don't want to do it ourselves, we can understand that someone else may be wanting to do this level of precision. Okay, so we want f of x0 plus h less than or equal to epsilon for 0 less than h less than or equal to delta epsilon. And this is to be found. So that's our variable. This is given. So the level of precision is given. How tight? Oh, I should have -0 so you know that we've got the limit in there. In fact, let me put -L then, that would be even better. -L, sorry about that. Okay, so we found x0, etc. So for us, this is square root of x is 3 plus h. That's, and then -3, not h, Grizzle. -0, we want to be less than or equal to epsilon for h positive. The 3's cancel, so this is just the square root of h less than or equal to epsilon. It's up to you if you want to keep writing this. Okay. I'm going to square both sides to remove the square root. And squaring, it's a monotonic function, so the inequality stays the same. And so now we know delta epsilon, okay? We started out, we want to meet this criteria, and the condition on h is that it needs to be less than or equal to epsilon squared. So delta epsilon equals epsilon squared, and we're done. So write down the definition, plug in everything you know, apply algebra, compute delta epsilon. So that works when the functions are simple enough, radicals, squares, etc. If there was a tangent, sine, etc., then all of a sudden you've got arctangents showing up and life becomes complicated. Okay. Questions on that? Is it sort of, kind of, a little bit Make sense? How about online? Everybody good? Okay, level of precision, find the bound on near x0 such that the level of precision is achieved. And if we can do that, we're good. Okay, so this one is a little bit more interesting. F of x, 2 plus e to the minus 1 divided by x plus 1. Okay, so this is more interesting. Is the function defined at x equals minus 1? And the answer is no, because this becomes 0, 1 over 0, so we don't want to divide by 0. So we need to use limits to understand what the function is doing as x is approaching minus 1. So let's first do the limit from the right, but if you want, we could start with the left, but we'll just start with the right. So we're looking at x goes to minus 1 through values that are strictly greater than minus 1, okay? And this is where it's important that as part of the definition, the function does not have to be defined at the point where you're doing the limit. Okay, so, whoops. x0 is here equal to 1. And L, we have no idea, okay? So let's go through the thought process. Okay, so examine f of x0 plus h for h greater than 0, h small. So let's do that. We have f at minus 1 plus h. That's 2 plus e to the minus 1, and then for x, we're plugging in minus 1 plus h. And then we're adding plus 1 to it. So let's do the algebra. These cancel. This is 2 plus e to the minus 1 over h. And let's put this data down. H positive, h small. Okay, so if h is positive, what is minus 1 over h? Negative. And if h is small, that is a very large negative quantity, and e to a very large negative quantity goes to 0. Okay, so that's how you work through these things. Okay, so the limit as x approaches -1 from the right of f of -1 plus h equals limit h goes to 0 plus of 2 plus e to the -1 over h, and so we just get 2. Okay, because when h is positive, -1 over h is negative, and as h gets small, e to the -1 over h vanishes. Okay, so it's pretty much the same thing, except now h changes sign. So we have f of -1 plus h is still equal to this. Whoops, I left out my 2. Equals 2 plus e to the -1 over h. That doesn't change. But this time, h is less than 0, magnitude of h small. H negative implies -1 over h is positive. H approaches 0 through negative values then. Implies that -1 over h goes to, drum roll please. Where's it going? Got an answer for me? Got an answer online? Where is -1 over h going? It's not a real number, okay? I'll give you that clue. Plus or minus?
Plus.
Plus! Give that man a treat. Oh, or a t. Wait, he already has a t-shirt, so he's already won the big prize. Yes, goes to plus infinity. So now the limit as h goes to 0 minus of 2 plus e to the -1 over h is equal to what then? So if -1 over h looks like an eta, which is the Greek version of h. Okay, so if -1 over h is going to plus infinity, then this is going to plus infinity as well. Okay, so bottom line, limit x approaches -1 from the left of our f of x equals plus infinity this time. Okay, so that's how you break these things down, okay? And the first one we did every epsilon, every delta. Here we went through the qualitative reasoning of how you break the problem down. So when you're asked to do a limit at a point, it's often easier, in fact, to first do a limit from one side and then the other. Okay, so that's, and it's, you know, it's unnatural for you because you haven't done enough of them, but with some practice, you'll get it. And so scan. write that here, plus. So you can get the formal definitions of what it means, but I think we've done enough limits that you guys have it. Okay, so we would formally have had to say, given an upper bound k, we can always go above it and stay above it if x gets sufficiently close to the limit point. So, and then it's also possible for these limits not to exist. We saw one of those. And kind of this is the classic one. I would draw it, but my drawing skills were a little bit weak. So this function is sine of 1 over x, and we're taking x goes to 0. So 1 over x is blowing up to infinity. And so sine is oscillating an infinite number of times, and you can check, you can see it in the book, that the limit from the right of this function does not exist. Okay, so limit from the right. If we approach x like this, the function is not settling down to a value. It just oscillates. So limit doesn't exist. Okay? How we doing? You ready to get up and leave, or are you going to stay and we can have a decent relationship when the lecture is over? Okay, so now here's the big payoff. Hopefully you think it's a big payoff. For me, it's a huge payoff. I want to define formally continuity at a point. And we're going to use it to help us simplify the computation of limits for functions that are continuous. Okay. So let's go back to our picture that we talked about even briefly last Wednesday when we first got started on this. I know it, you know it, so everyone knows it. This point is a problem because there's a jump, okay? This point is a problem, okay? There's a jump. This point is not a problem. This point is not a problem. This point is not a problem. We have continuity at a bunch of points, and there's only 2 of them where there's an issue here. What makes them special, okay? What makes them problematic? That's all we want to understand. The limit from the left is not equal to the limit from the right, so there's a gap. That's called a jump. The function is discontinuous. Okay, we get it. Here, the limit from the left equals the limit from the right, but it's not equal to the value of the function. That's a problem. It's not continuous there. And those are the only problems. So we're just going to put that into a definition, and because you know limits decently well, okay, you now have a formal notion of continuity. Limit from the left equals limit from the right. They both exist, and they equal the value of the function. It's that simple. Now, is that the equivalent to I can draw the function without taking my pen off the screen, etc.? Pretty much, but it seems a little bit more formal than what your teacher taught you in high school, okay? So let's be good and write this stuff down. Continuity at a point, and let's give that point a name. X0. So we have f takes an interval AB to the reals. For our definition here, X0 is not one of the endpoints, and you'll see why in a second. And we'll talk about how you handle endpoints, but it's not it's not very hard either. So X is between the two endpoints. F takes AB to R, X0 between the two endpoints is continuous. That's a U, even I couldn't tell. Continuous at X0. The limits from the left and right at X0 excuse me, I've got it written better in my notes than what I'm writing it in my head here. Left and right at X0 are finite equal and equal the value of the function at X0. So let me see what you like better, the words or the formulas. Limit x goes to X0 from the left of f of x equals the limit x goes to X0 from the right of f of x equals f of X0. Okay, so me, I like the formula, and then I try to turn the formula into English and I mess it all up, okay? So the formula is precise and captures everything you want. Limit from the left, limit from the right, and the values of the function. They're all the same. Okay, so now I'm going to try to draw a graph. We're going to apply this definition. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. We don't need to go to 9, but I've got it. And 1, 2. Okay, so go away. Okay, so at 1, we're going to have one of these guys Got it, whatever you're doing. And then, okay, so I'm going to try to draw a straight line to roughly 3. So this is fine. Another missing hole. I don't know about you guys, but that's hard for me to do these kind of drawings. Okay, so the circles means the function is not defined there. And the big dot here means at 8, this is the value of the function, okay? So, determine if f is continuous at the following points. Answer just yes or no, and a brief why. Okay. First point will be x0 equals 1. Second point, I've got x0 equals 3. And then the last point, x0 equals 8. Okay, we'll do this and then we'll take our break. So these are just an itemized list, these little dots over here. Okay, so the last point was 8. Okay, so x equals 1. So on your sheets of paper, just kind of write down what you think. Yes, no, for each of these 3 points. And then using this formula, I suggest, in other words, visually look at limits from the left and the right and compare them to the value of the function and say all of them are satisfied, something fails, it would be discontinuity, etc. Okay? So I'll give you 2 minutes. We'll solve it in 1 minute, then we'll take our break. And I'll call on Luke and Jason to get things started since they've been shielded from my wrath as we're talking about limits. One more minute. Yeah, it's fine to talk amongst yourselves. Daniel, talk to your neighbor, get some help. What happened to Zoe? I don't know, we got to fix that. Okay, Jason, x0 equals 1. Is our function continuous at the point 1? Put it into the chat, please. Jason has his Zoom on, but he's not present. Luke, oh, not defined, thank you. The function is not defined, and so in terms of continuity, what does that mean? Is the function continuous at 1? So your answer is going to be no, and the reason is, let's see, the limits both exist. But the function is not defined there, so it can't be continuous there. Thank you. We're doing continuity at a point. The only thing I'll add, Jason, to your statement. So eventually we will define continuity on an interval, and if a function fails continuity at any point, then it is discontinuous. So you know way too much, Jason, so you're half an hour ahead of me. Luke, x0 equals 3. Continuous, not continuous, and why? Is continuous, so yes. Oh, you're worried about the cut? That would be for differentiability, okay? So why is it continuous? Limit from the left, limit from the right, value of the function, they all agree, okay? Limits from left and right equal value of f at x0. Perfect. And then, I don't know, I'll go with the folks farthest away from me. At x0 equals 8, is the function continuous there? No! And why is that? Yeah, limits from the left and right, even though they exist, they disagree. Yeah. Now, if they didn't, one of them didn't exist, it's discontinuous as well. So, yeah. We can stop there. We don't even have to compare them to the value of the function because there are 3 conditions that have to hold, and if any one of them fails, then it's all over, dude, okay? Okay, we'll take our break. So let's continue with just a few more examples. Whoops. x0 equals 1. And here's a function that blows up, okay? So is the function f of x equals 1 over x continuous at x0 equals 1? Justify your answer. And then what about x0 equals 0? Ooh. Let me get another one going, and then we'll work these together. f is going to take the interval 1, 2 to the reals. Here's 1, and here's 2. So the function can do something squirrely, but then we're going to make this open, and then it starts blowing up. So it does not include the point 2. So we're interested on the right, whether it's continuous at the points 1 and 2, and I've excluded 2 from the domain. And then over here, we're looking at x0 equals 1, and then x0 equals the origin. Okay, so what do you say? Is the function continuous at x0 equals 1? I see a nod, okay. The value of the function, limit from the right, limit from the left, they all agree. So yes, for x0 equals 1, and it's limit x goes to 1 from the left equals limit x goes to 1 from the right equals f at 1. Okay, we did the easy part first. What about at the origin? Is the function continuous at the origin? I got a no and not sures, okay? Is the point 0 in the domain of the function? The answer is no, the way I've drawn it. You know, if I added a point here, then it's in the domain, but we still have discontinuity, okay? So, and the answer, and then no for x0 equals 1. And what would be the reason if I add 0 into the domain, why is it discontinuous there? What about the limit from the left? You don't, yeah, so you don't have to worry about it because it's an endpoint. The only limit that makes sense is the one from the right, but it doesn't agree with, it's not even finite, so it can't be continuous there. So it's no for x0 equals 1, and this is with f at 0 equals 0 defined. Because limit as x approaches 0 through positive values of f of x is plus infinity, and that's certainly not equal to f at 0. Okay, so awesome. So here's another function where this one I've excluded the second endpoint. And then, so is the function continuous at 1? I see a yes. Even though it's an endpoint, so we don't look at the limit from the left, because that's not part of the domain of the function. We can't evaluate that limit. The limit from the right agrees with the value of the function. So, yes, for x0 equals 1, that's because limit as x approaches 1 through bigger values of f of x equals f at 1. We ignore the limit as x goes from 1 from the left of f of x because f is undefined for x less than 1. Okay, so you guys can be better than all of your other compatriots in your engineering courses at these. And then the problem at 2 is that 2 is excluded from the domain of the function, so we can't talk about limits there. Okay. And no for x0 equals 2, because 2 is not even in the domain of the function. Okay, so I gave you some kind of tricky reasoning here. So the key point for continuity at endpoints of an interval only check one-sided limits that are in the domain of the function. Okay, so you just have to be reasonable. Wow. Okay. Now we're going to anticipate, we're going to give a definition that Jason anticipated for us. So definition, f takes some interval I to R for I equals, could be open at the two endpoints. It could be open and closed on this one. Could be closed and open on this one. Or it could be closed on both ends. So a function from any of these types of intervals that we often see in the reals, half open, half open, half closed, fully open, fully closed, is continuous on I if f is continuous at x0 for all x0 in I. Otherwise, it is discontinuous. So it only takes one point to make a function discontinuous, okay? Because it has to be every single point for it to be continuous. U-O-U-S. Discontinuous. Boom. How are we doing? Make sense, this stuff now, kind of, sort of? Yeah. Okay, so we've got a little more refined than you can draw the function without lifting your pencil from the paper. So what I want to just paste in now, I need a lot of room, is just a list of common continuous functions that we see in engineering. Okay, so this is a table in the book, proposition 4.18, I should say. Come on. Okay, I'll flatten you, so yes. Now I can do all this stuff. So these functions are continuous everywhere unless indicated otherwise, and you'll see what that means in a second. So a constant function, continuous everywhere. Linear functions, continuous everywhere. Quadratics, higher degree polynomials, they're all continuous for every point in the reals. Sine, cosine, yes. Tangent, except where cosine vanishes, okay? So it's sine over cosine, and we have to avoid the odd multiples of pi over 2. So tangent of x works. Power function, whoops, x to power y over here. If x is positive, then, and y can be any variable, but it's a constant here, so we're looking at the x varying, y is fixed, but can be any real number. As long as x is positive, then the function is continuous. So it's continuous on the open interval 0 to infinity. Exponential functions. Doesn't matter whether it's the unnatural exponential and unnatural exponential or the natural exponential. It's good. The logarithm, we need x positive because we're inverting this. And if a is bigger than 1, this is always positive. E is bigger than 1, that's always positive. So the inverse, its domain has to be the range of these exponential functions. Rational functions, we see those all the time, and they're continuous everywhere except points where the denominator vanishes. And so the denominator, if it's a polynomial, it has a maximal degree. Let's say it's 17, so it can have at most 17 roots. And then we only care about the real roots because we're working as a function to the reals. If it vanishes at the imaginary unit I or minus I or 3 plus 2I, we just don't care. We're only worried about roots that are in the real numbers, okay? So as long as the denominator is not vanishing at a real number, all other points, rational functions are continuous. Roots, they really fall under the power things that we were talking about. Square root of x, x is positive, Cube root, we typically allow x to be negative and say the cube root of -1 is -1, okay? So these integer roots, when the integer is odd, you can allow x to be negative. And then there's other special functions like the absolute value. And yes, it has a cusp, and that's going to mess up differentiability, but it's still continuous. This tri is the triangle function. Just don't mess that up. Okay, and so the unit triangle function is -1, +1, and 1, so its area is 1. That's the triangle function, and it's 0 every place else. So this is tri of x. You guys worked with radial basis functions in Rob 101, and it's the same thing as the Gaussian or standard normal distribution. So tons of continuous functions. Okay, so do discontinuous functions arise in engineering? So everything we've been doing for real, or is it just nonsense because those cases never happen? And I'll put real engineering, okay. So that means engineering that's not done in my head, so some fantasy that a faculty member comes up with, okay? That's what real engineering is, stuff that you guys will go out and do. Unless you become a faculty member like me, which is a perfectly fine objective. I would love to see some of you guys follow that path. And the answer is yes. So we use algorithms as functions all the time. So I have a function on my robot that's planning how it's going to go from point A to point B. Cool. Now it comes to an obstacle. And suppose it comes to this obstacle straight on. It has to turn left or it has to turn right. Guess what? That's a switch. And switches are discontinuous, okay? So algorithms are functions, branching, which is what I just described there. Can lead to discontinuities. So robots can cause jumps. So here's things that, young students working in a lab, whether you're a grad student or an undergrad, happens in my lab with the Cassie robot. One of the students asked them to go over and turn on the robot, okay? Powers it up. Now, what if the person who wrote the control laws on it didn't say when the robot is first turned on, keep the motor torque at 0? And somebody moved the leg here, and the set point for the leg is over here. What's the controller going to try to do? It's going to try to move the leg over. Now, when that happens at something that looks like it's about to break the speed of sound, it is scary as all get out, okay? So, when you are writing the code for those robots, you've got to be very careful on the startup sequence, okay? Otherwise, you just turn the power on and you enable all of the motors and everything. Who knows what state the last reading of the encoder was that's being input into your algorithm, okay? You need to read it and then have a little ramp that takes you there at a slow rate, which means you need to build in continuity into your algorithm. This is a big one. In feedback control, we use step functions as set points. As set points. Let me describe that. So you guys take Rob 311, and you've got this ball bot. And you're steering your ball bot down the hallway. And then coming from the other way that you can't see because they're around is somebody else's ball bot. So what are you going to do? You're going to slam the speed control as quickly as you can to 0 or even negative to avoid your robot and that other robot getting destroyed, right? Who was supplying the step function? You. You're moving down there at 3/4 of a meter per second. You see danger and you go, whoa. I mean, it's just like this on your little controller, okay? But you provide it. You are the discontinuity. Okay, so there's plenty of discontinuous functions in the real world. Questions? Now, if you get to the chapter 10 and you read the subtle points that I put in there, which I think no one last semester did, okay, so maybe you guys will. There's some tricks of the trade to filter the commands so that you at least make the robot less discontinuous and jumpy. Okay, so, but it takes experience to know how to build that into your software. But it's there, okay? So you can take the command and then you can ramp down at a controlled way. The thing with these ball bots, it's sitting on a basketball. You jerk it more than 4 degrees, it spontaneously disassembles from the basketball. It just falls off, okay? But in SpaceX speak, it spontaneously disassembles. That's what they said with all their rockets were blowing up. Okay. We just have a few more things for today, and we'll call it quits. So if you're doing a limit from your right and a limit from the left, and all you really care, where you care about both of them, you can just talk about the limit at the point. So it just means that you've done left and right. So these are two-sided or double-sided limits. Okay, so we say the limit as x goes to x0 of f of x equals L when the two one-sided limits agree. Okay, so instead of having to write down that the left limit and the right limit both exist and agree to something, you can simply talk about the limit as x approaches x0, and that means from the left and the right. Okay. How many of you have watched the channel 3 Blue, 1 Brown? A lot of you have seen 3 Blue, 1 Brown. Okay, so I've got the video linked, and you'll be able to just access it when I post these notes. We're not going to watch it because it's, I don't know, 15 minutes long or something. 18 minutes long, so we're not going to watch it. But it covers a lot of cool things, and something that if you're uncomfortable with these epsilon delta definitions,
I want to take some time to talk about.
I recommend you go through the video. We won't cover L'Hopital's rule for a couple more weeks, okay? For another 2 weeks or something.
That it's a matter of assigning fancy notation to
But
the intuitive idea
it
of one value that just gets
redoes what we've done in slightly different terminology, so in case you'd like to just firm it up. And besides, this guy's videos are just kind of amazing. I mean, the level of
typically predicts. To be honest,
animation and everything is something that,
if you know what the word approach means,
my pies don't have eyes on them. I mean, mine.
you could say the idea of a limit is not really
So
anything
no faculty member can compete with these types of videos, but I think they can be very helpful, and so it's linked at the very beginning. So come on back, my notes. Come on back. It's linked at the very beginning of the lecture. It's also in the textbook, of course, but maybe there's too many videos linked in the textbook and you won't be able to find the right 3 blue, 1 brown. Okay, a list of functions that are continuous. What happened? Okay, calm down. Yeah, so highly recommend that 3 blue, 1 brown video as supplemental things. The other resource you have is you just go to U of M GPT and say, hey, I'm struggling with left limits or right limits. Give me the formal definition, give me the intuitive definition, give me examples, let me provide answers and you provide feedback. So if you start creating these more complex prompts, you can get some really nice practice sessions there. Okay, so what is the big payoff? Doing limits so carefully. Okay, so the answer is that many functions compositions of simpler functions. And so oops, let me put an argument in there, f of h of x. Suppose it's the composition of f and g. So that could be pretty complicated. But suppose I wanted to take the limit as x equals x0 of this complicated function. When can I take the limit inside the function? And how could that help? Well, supposedly this is something fairly ordinary, and we can evaluate the limit straightforward. The limit's going to be a number. This guy's a little bit more complicated, but we just have to plug a number into that function and we're done, okay? So that's why you would like to be able to take the limit inside the function. So when can you take the limit inside the function? So it's a divide and conquer strategy. Well, the answer is almost here. Okay. Two-sided limits, we're just taking the function. And then we had our definition of continuity back here. So we can either take two one-sided limits or we can just make this one limit. The limit outside the function, well, as x goes to x0, there's inside the function. When does that work? When the function is continuous at the limit point. It's part of the definition. It's kind of baked in, okay? It's baked into the definition, so. And where did I stop writing? I have no idea. Everything erased. Where'd it go? There we go. Okay, so proposition. If one limit x goes to x0 of, not f of x, g of x, it's going to be the inside one, equals y0. And two, f is continuous at y0. Then limit x goes to x0 f of g of x can be evaluated by taking the limit inside the function. And it's essentially the definition of continuity. But you can't get that from the definition of continuity where you draw the function and whether you don't pick your pencil off the paper, okay? So you have to understand continuity in terms of limits to be able to bring and interchange doing the limit and evaluating the function. So let's just see a few examples and then we'll go home. So this first one will be easy. So, example, easy. Compute the limit as x goes to pi over 2 of 3 plus sine of x sine squared of x plus 4. Okay, so the strategy on these is we need to figure out what is f and what is g. Does that look like f composed with g? Maybe. What if we let g of x equal sine of x? Is evaluating the limit as x goes to pi over 2 of sine of x going to be an easy calculation? Yep, it's plus 1, okay? Let's let f of y be 3 plus y over y squared plus 4. That's a y. Is this continuous at y0 equals 1? Yeah, it's continuous everywhere because this has no real roots. It never vanishes for any real number y. So this is a continuous rational function. And hence, whoops, the limit as x goes to pi over 2 of f of g of x is just 3. So this is y0 plus 1 over 1 plus 4, 4/5. Done. Okay. So you take something complex, and break it down into easy things that you know by inspection are continuous, and that saves you from having to show this function is continuous, and that function was not on our table of known continuous functions that engineers see all the time, okay? And there's lots of f composed with g's that are like that. Well, this one is more challenging. So you're given this. We know how to define Euler's number. 1 plus 1 over n to the n equals E. Evaluate limit n goes to infinity 1 plus x over n to the n. It's enough to do it for x positive. Okay. So what I love is that you guys give it a crack, and then Wednesday at the beginning of lecture, we'll see what kind of different approaches you took on it. Okay, so just take a crack at it. Okay. So when you have a 1 here, you get E. When you have an X here, what do you get? So you have to make a guess. Okay? And we'll see how close you get to it. And if you don't get so close, I'll give you some hints and we'll take it apart and we'll work it out on Wednesday. So that's it. That's all I have for you today. I think it's enough. I've reached the limit from the top of your patience, okay? So I don't know, we've done left and right limits, now we got to do up and down limits. So I think from the limit from up of your patience has reached 0, so we're done, okay? We're done. And thanks for coming, thanks for taking the t-shirts, and yep, those of you who are online and would like to be physically present to collect a t-shirt, Max and I will do our best to get them here. Yeah. And we're confirmed that Project One is working now, right? So yeah, so anybody who had difficulty with Project One is now fixed, and all I can say is, sorry.
The other 2 projects are good.
They're good too? Okay, projects 2 and 3, they're not released, but when they are, they're gonna work, so that's good, okay?